Okay, so this meeting is being recorded. So welcome back to Chemistry 2330, Introduction to Organic Chemistry. We're going to finish up chapter 12 today, which is aldehydes and ketones. But first, a little administration. For this week, we have the full uninterrupted videos are on YouTube. So those are available to you. We have the goals slides that are available on Top Hat. Don't forget to do the Top Hat homework. It's due Friday, November 6th at midnight. Okay, so all of those things are going to be kind of due this week. And those of you who have lab, please read your emails carefully. Those come out intermittently. In fact, the lab group C, I believe, came out this morning, so that you have a new updated way to get those lab information done. Your lab instructors and I are trying to get everything graded and up to date by next Monday. So if there's still a couple things missing this week, don't worry about it. After next Monday, go ahead and double check to make sure we have as many things as you did put in, and then hopefully the grade book will be fleshed out and correct at that time. Okay, that being said, do we have any questions about administration or the class in general before I continue on with chapter 12?
I have a question.
Yes.
So in regards to lab, I was watching like the YouTube videos from the lab, and I believe like the instructor for that lab was, I remember like they were asking about a data sheet, and they said no, but then I saw on my grade on the on Canvas, I got deducted points because I didn't add the data sheet.
Was there a data sheet in the laboratory manual?
I don't have it off the top of my, or like I don't have it on hand, but there very well could have been.
Okay. In general, if there's a data sheet in the lab manual, that is something you do fill out. The the SN1, SN2 is a little different because there wasn't a data sheet for SN1, SN2 for the specific reaction you ran in lab itself. But
okay, gotcha. Thank you.
When you figure it out, just send me an email and see if it is something we need to discuss further. Okay.
Thank you.
All right. So what I'm going to do is I'm going to go ahead and start sharing my screen. Let's see. Let's put this up over here today. Sorry if you hear bassoon in the background. My daughter has online band, so you might hear that. So it's actually a really cool sound, so I don't mind it at all. Okay, so when we talked last time, we talked about aldehydes and ketones, and we were talking specifically about the fact that it has its reactivity is all based on the idea that the carbon is partially positive, the oxygen is partly negative. That gives rise to its physical properties, its dipole-dipole interaction, plus how it reacts with some chemicals, okay? We also figured out that that carbonyl compound having that partially positive carbon makes the hydrogens adjacent to it more acidic, and we can actually undergo this ENO keto tautomerism. And that gives rise to reactions that we don't think should happen, but we know they happen because of not only because of racemization of stereochemistry, for example here, but also with this reaction at that alpha site. So the alpha site is the site next to the ketone, okay? So we get these reactions there. And so we know this happens, and because of the way the mechanism works. So that was really an interesting way to start our aldehydes and ketones in the fact looking at those two types of reactions. There's a reaction at the carbonyl center, and then there's a reaction at the carbon next to it if there's a hydrogen there that can be moved around during an ENO keto tautomerization. Okay. So now what we're going to do is we're going to talk about how to make ketones and aldehydes and what kind of reactions they end up doing. Okay, so aldehydes are, it is possible to oxidize aldehydes all the way down to carboxylic acids. In fact, we had to have a special reagent. When we looked at alcohols, we had to have a special reagent to stop the reaction at the aldehydes. Remember, if we had a primary alcohol, we had to use PCC, pyridinium chlorochromate, to stop it at the aldehyde because it could be further oxidized. Now, if we had that same primary alcohol and reacted it with, like shown here, chromic acid or any of the chromium type oxidation chemistries, it goes all the way to the carboxylic acid. And so the carboxylic acid, which we have a whole chapter on, and we'll talk about that soon, has this carbonyl in it, and it's the most oxidized our carbon can get. The only thing that's even more oxidized than that would be CO2. That's as oxidized as you can get a carbon because it has 4 bonds to oxygen. Okay, so the idea is that the aldehydes will actually slowly oxidize just with air to get to our carboxylic acids. But to do it quickly, we use that chromium species here. In addition, we can heat it with a little bit of oxygen, i.e. air, and we can convert it 2 equivalents of your aldehyde, react with 1 equivalent of oxygen to convert it all the way to the carboxylic acids. So that's one way to generate carboxylic acids from aldehydes, okay? But the idea is the aldehyde itself is being oxidized by those oxidizing species. Okay. So when we have ketones, because there's no hydrogen right there, we'd have to break a carbon-carbon bond, okay? So it rarely oxidizes except in special cases, okay? So in the aldehyde, like in the case of our alcohols here, we were just breaking hydrogens to turn them into aldehydes and ketones. So that would give us an aldehyde, and if we moved our OH over here, we would get a ketone just by doing that oxidation, and the reaction stopped, okay? Now, it's because that ketone is pretty stable. However, under certain conditions, we can take advantage of that AgNO ketotautomerism and oxidize them even further, okay? So we can go from our secondary alcohol to our ketone here, but in the case of this particular reaction here, we're using nitric acid as an oxidizer at a very high temperature. Now, again, the ketone itself does not oxidize. We have to wait for this enol form. Once we get this enol form, we actually are oxidizing the alkene. And the alkene is oxidized. And if we oxidize that alkene, that means we're going to break the double bond, giving us a carbonyl compound on each side. And so in this case, because we started with this cyclic right here, we end up with 2 carboxylic acids on either side. Okay, so that's a special oxidation of alkenes. We also did oxidations of alkenes in that alkene chapter where we were able to make aldehydes and ketones and carboxylic acids. So this is a way in which we can actually get a ketone to do that same type of alkene cleavage. Okay, so another cool thing is that in the beginnings of chemistry, you know, in the biggest push of industrial chemistry, it started in the 1850s in Germany and transported to the United States around 1860s. We didn't have these fancy instruments, the IR and the NMR. These had not been made yet. So what we did is we used a lot of what we called qualitative tests that would react to specific functional groups at a specific time. We've seen that in lab, like pH indicators change color. It's a physical change we can measure without an instrument. We can do also a way to test for aldehydes is what we call the silver mirror test or the Tollens test. So in this case here, we know aldehydes can be oxidized, right? They can be oxidized from that aldehyde to the carboxylic acid, okay? So what if we used a reagent that when it oxidized, it gave a visual indication of change? So in this case, we're doing that. We're using this silver nitrate, and this is silver 1. Okay, so it needs 1 electron to become silver metal. And so it's silver 1, and it's in the presence of base. And so when we have that reagent dissolved up in solution, it creates, with this ammonia here, it creates a complex right here, okay? This complex is water soluble, okay? This ammonia silver complex is water soluble. Now the cool thing is that if we place that silver water soluble complex in the presence of an aldehyde, The silver wants to go back from being silver 1 to being silver 0. It wants to be silver metal. So it does this by oxidizing the carbon that the hydrogen has on here and converts this silver to silver metal, okay? And when it does that, it uses water in the reaction to make it a carboxylic acid. But the brilliant part of this is that the silver metal almost always deposits out as a film of pure silver on the inside of the test tube. Okay, so literally you can see yourself in the silver mirror. And so it's called the silver mirror test, or it's really using Tollens reagent. It only works with aldehydes. This oxidation does not happen with any kind of alcohol. It does not happen with any ketone. It only is specific to aldehydes. Okay, so that's one of the really cool things. And what we'll see in lab and a couple of the other ones, you know, some of those reagents only work with some kinds of sugars, and some only work with aldose sugars, some will only work with ketose sugars. And that's that same kind of concept where it reacts in a specific way with a specific kind of compound. And we see this in this Tollens reagent. Okay. So that's how we can oxidize. Since ketones really don't oxidize unless it's in that ketone and we break it apart. So, and the aldehyde only goes to the carboxylic acid. Let's go the other way. Let's reduce them back to what they were before. Okay, so we did, when we did the alcohols chapter, we oxidized primary alcohols to aldehydes. We can do the reverse reaction, okay? And aldehydes will give us primary alcohols because the oxygen here is on the end of the chain. And so if we added a hydrogen here and a hydrogen here, we would end up with a primary alcohol. Okay, now we can do that same thing. We can add a hydrogen to this side of the carbonyl and this side of the carbonyl on a ketone, and we'll get a secondary alcohol. Okay, but not all reagents do this. We use a specific class of reagents to do this kind of thing. And it has everything to do with the idea that the carbonyl is partially positive carbon, partially negative oxygen. Okay, so it can be done with just hydrogen and catalyst, but it takes a lot of pressure and a lot of heat. Okay, so in the case of this right here, where we use hydrogen, hydrogen's a non-polar molecule, so we have to activate it with this and really hit it really hard to try to get it to do that. Unfortunately, it'll also reduce down any other alkene or alkyne in your system. So we want to have something that's very specific that just reacts with carbonyl compounds to give us just that reaction on the center. So imagine we wanted to go to having this be, instead of being all the way down to the alkane, we actually wanted to form this alkene. We would need a reagent that only attacks the carbonyl. And that's what we're going to do next. Okay. So to be very specific and only attack that, we do what we call hydride reductions, and they're called metal hydride reductions. Okay, so we have a metal that participates in the reaction, but the big part of the thing is the idea that we are adding a hydride. Okay, so what's a hydride? Okay, so if we have hydrogen with no electrons around it, it's hydrogen plus, right? So that never happens. It's always as a complex, you know, hydronium ion, right? And then if we have a hydrogen with one electron, it's hydrogen elemental, and it usually dimerizes to form neutral diatomic hydrogen. Okay, what if you have two electrons? You fill that s orbital, and you have two electrons in there, and it has a negative charge. That is our hydride ion. It's a negatively charged hydrogen with two electrons on it. Okay, so this is our reactive species in our system. And because it has a negative charge, it's a very strong nucleophile. Okay, so what these look like is we have a complex where we have 4 hydrogens on a boron, and then we counterbalance with the positive sodium charge. Okay, now if we think about it, we know that the hydrogen attached to it has a negative charge, because when you have, normally boron wants to have 3 bonds to it. And so neutral boron with hydrogen on it would look like this, okay? But by adding that next bond to it here, that means both of these electrons are from the hydrogen. to give us our net negative charge here and to give it a counterbalancing metal. Now, that's not the only one. We can do this with aluminum too, okay? So in this case, we usually use lithium as the counterbalancing metal, and we have aluminum hydride. So again, we have 4 hydrogens on that lithium, on that aluminum metal, okay? But the active ingredient, the thing that does all the work, is this hydrogen with a negative charge. Okay, so let's talk about the selectivity of the sodium borohydride, okay? Now, sodium borohydride itself is like a little powdery solid, and typically you dissolve it up in an aqueous solvent like methanol or water. The reason we do that is that this reacts directly with the borate to create this boron salt, okay? And it helps to do the reduction, okay? So the other thing that we want to do here, so basically this is the boron ends up reacting with all of these alcohols as it loses all of those hydrides. Okay. So a hydride leaves and then it forms an alcohol boron bond, but it has 3 more hydrides to transfer. So then another hydride will leave and it's got 2 alcohols on it and 2 hydrides. It still has 2 hydrides to transfer. So that means we can have 4 carbonyls reduced with just 1 equivalent of sodium borohydride. And then that's going to end up creating a whole bunch of this intermediate here, which is a stable salt. And then we have to actually decompose it with water at the end to generate our primary alcohol. Okay, so how does this work? Okay, so the key step in this metal hydride reduction is that the hydride is going to use its electrons that are right now forming the sigma bond with boron, and it's going to attack the partially positive carbon, creating a new sigma bond. When these electrons come in, the electrons in the double bond have to kick out, giving us a negative charge on oxygen. So this is a nice covalent bond, a covalent sigma bond now, right here. Oops. Right here, we have a covalent sigma bond with our hydrogen, and we have a charged oxygen species. And it just happens to counterbalance with the rest of the boron complex. Okay. But notice, there's still 3 more hydrides left. So this is going to react again to give you another one on there, and it'll react again to give you another one on there, and again to give you the 4th one on there. So it will keep reacting with aldehydes or ketones until it has 4 different groups on that boron. Okay, and then once you decompose it, what happens is we break this bond with water and giving us a hydrogen going to the oxygen there, giving us our alcohol, and the OH is going off to the boron to give us some kind of boron salt. Okay. Okay. So the key step here is our hydrogen with a negative charge is attacking our partially positive carbon, giving us our intermediate complex, and when we decompose it with water, we generate our alcohol. Okay. So it's very specific. It will not react with an alkene because that carbon-carbon double bond is not polar. It will react with a carbonyl because the carbon-oxygen double bond is polar. That's why we get selectivity of this reaction. Okay, so if we get selectivity of that reaction, then maybe we could use a different reagent for different things. Okay, so for example, these metal hydrides, I already said this, but will only reduce down aldehydes and ketones. The sodium borohydride will only reduce down aldehydes and ketones and will not touch any alkene in the system. Okay. So if we actually wanted to reduce down the alkene, we have to use that trick of making that carbonyl no longer polar and making it into an acetal. So you can selectively choose, I want to react that ketone or aldehyde. If I do, I use sodium borohydride and boom, we're done. Oh, no, wait, I want to get rid of the alkene. So I need to protect my carbonyl compound as an acetal and then do a regular reduction of an alkene. And then by clipping off our acetaldehyde, we can get our carbonyl compound. So we're finally to the point where we have enough reagents we can selectively choose which functional group we start with, which functional group we'll have at the end. Okay. So so let me go back, and there was one, I thought I had one more slide here. Okay, so we have sodium borohydride and a lithium aluminum hydride. They both reduce down aldehydes and ketones to primary and secondary alcohols. Although lithium aluminum hydride is stronger, and what we'll learn in the carboxylic acids chapter is that we can start using this to reduce down things like carboxylic acids and stuff, but this won't do it. So we're introducing both of these hydride transfer agents here because this works with aldehydes and ketones, and this will work with harder to reduce substrates. And we'll see that selectivity in the next chapter. All right, questions on reducing or those reactions we've talked about so far? Okay, so what I want to do for the rest of it is I want to pull up my goal slides for aldehydes and ketones and specifically look at goal number 3 of the goal slide, okay? In goal number 3 of the goal slide, we're talking about the different reactions, okay? So nomenclature, we talked about that already, keto tautomerism. And remember, there's 3 reactions associated with that. There's that alpha halogenation reaction, there's the racemization of stereochemistry, and then there's that oxidation of nitric acid. Okay? So those are the 3 reactions we use with the keto tautomerism. But let's look at the rest of those reactions again to kind of solidify the selectivity and the types of reactions they are available to us. And the first one was we actually created a new reagent to create our first carbon-carbon bond by a reaction, okay? And that carbon-carbon bond was created by a Grignard reagent, okay? So Grignard reagent is when you create that negative charge on carbon, and it's a very strong nucleophile, and it attacks the partially positive carbon of our aldehyde or ketone. Okay. And it has everything to do with you're actually forming a very polar sigma bond, but instead of having the carbon being the partially positive side, like in a carbocation, or when you have a leaving group like bromine, where the other side is the negative side, we've actually reversed the electron demand. We have the carbon being the more electronegative atom, and the metal being the more electropositive atom. That gives rise to our carbon as the anion. Now that we have that anion, we can use it as a nucleophile. But because it's such a strong base, we cannot use it in the presence of any protonated solutions or alcohols or water. So no water, no alcohols, no carboxylic acids, nothing with a hydrogen that can hydrogen bond or be removed by a strong base, because that will react. So we have to be very specific about our reaction medium. And typically we use ether or THF. Those are the 2 things that you'll almost always see these reactions done in, because they don't react with the system. Okay. So if we take our Grignard reagent and we react it with formaldehyde, that formaldehyde already has 2 hydrogens on there. We create a new carbon-carbon bond between this anion and this partially positive carbon. And then once we add acid at the end, we end up generating a primary alcohol. So you can take any Grignard reaction and formaldehyde and get a 1 carbon extension and a primary alcohol. You're going to be adding 1 carbon and making a primary alcohol. So this is really cool. Let's say you had sorry, let somebody in here. Let's say you had propyl chloride, right? And you actually wanted butyl chloride, or you wanted butyl alcohol, and you had propyl alcohol, okay? So you want to add one carbon to it, okay? So what you could do is you could take your propyl alcohol, react it with thionyl chloride to make it the alkyl halide, and then oh yeah, no, you can take your propyl alcohol, oxidize it to the aldehyde using PCC, and then attack it with a Grignard reagent to, no, we want to make the Grignard, sorry. Let's say you wanted to make 1, 2, 3, 4 butyl alcohol, and all you had was propyl alcohol, okay? So the way to do it, I was right the first time, is you would make the alkyl halide from this using thionyl chloride. You'd make the Grignard reagent, and then you would react that Grignard reagent with formaldehyde. If you reacted it with formaldehyde, you're adding that one extra carbon to your chain, and it's going to give you that primary alcohol. Okay, so formaldehyde always leads to a primary alcohol and one more carbon on your Grignard reagent. So let's say we already had an aldehyde that had an alkyl chain on it, okay? If our aldehyde has an alkyl chain on it, we're gonna add one more carbon bond, giving us a secondary alcohol, okay? So it doesn't matter which groups we have here. All you need to know is you have the Grignard of one and the aldehyde of the other, and you can make a secondary alcohol. Now, if you already have a ketone and react it with a Grignard reagent, you always get a tertiary alcohol, okay? So you're adding carbon bond each time. Formaldehyde had no carbon bonds. It made a primary alcohol, that's one carbon bond. The aldehyde with a long chain already had one carbon bond to it. You added a second carbon bond, giving you a secondary alcohol. In a ketone, you have two bonds to carbon. You're getting another bond and making that third bond to carbon, making a tertiary alcohol. So that's the great thing about Grignards. You can choose and pick which way you want to go. And as we discussed last time, you can actually go through, this and make this by several different reagents. You just have to know which aldehyde or ketone you want to start with. Then we learned about the hemiacetal, but the more important part of that was when we added two alcohols across that carbonyl compound and made our acetal. We also learned that cyclic acetals are more stable, and therefore they are more useful in chemistry. And so when we do that, we typically form our cyclic acetal by using our carbonyl compound, R and R, plus some alcohol, some diol. And that's going to create our cyclic acetal that takes away the reactivity of that polar bond, and we can do other chemistry on the system. You can now make a Grignard reagent on that substrate. You can attack a different species. You can reduce down. You can do all sorts of things because you've taken away that partially positive carbon. So that's a good way to, quote, protect our group or give us an ability to do other reactions. The other thing that we found out that carbonyls could do is we could lose water and generate a nitrogen triple bond. I'm sorry, double bond. In this case, all we're doing is we're taking the oxygen from the carbonyl and the two hydrogens from the primary amine and losing water, creating a new carbon-nitrogen double bond. Now, this is synthetically important because it's very hard to get a secondary amine using SN2 reactions because it continues to be a nucleophile after it reacts. In this case here, once we form this species here, we can then react it and stop at that secondary amine. And this is just the mechanism. So we can take that once we make our imine here, our double bond here, we can reduce that down and get a secondary amine. It's the only very clean reaction we have to get to a secondary amine. And then, of course, we talked about oxidation. Aldehydes will reduce down to carboxylic acids. Ketones don't oxidize unless there's a special reagent with nitric acid and the eno keto tautomers. All right, questions on that? So we just talked about all of those reactions there. Okay. Questions on chapter 12. I'm going to go ahead and upload chapter 13. And we'll see about starting those up.
I have a question about chapter 12 homework.
Okay, yes. Ask away.
So the homework problem was problem A and K 8.
Okay.
You had a chart in the full length slide. And I was wondering,
Okay. Apparently I'm doing too many things at once because I'm not getting your whole question. Here, let me stop the video. Hang on, and let me stop the video. And I should be able to hear you. Okay.
Okay, so it,
Can
you hear me?
Yes, I can hear you now.
Okay, so it was question A and K 8 on the homework 12. And basically it was just, what would you expect to have the lowest boiling point? And you have a slide that pretty much lists them all in order with the boiling points. And I was just wondering why diethyl ether on the slide shows the lowest boiling point, but in this question it says it was wrong.
Let's see, lowest boiling point. I'm still speaking here. Which of the compounds below would you expect to have the lowest boiling point? They all have approximately the same weight. Okay, so butane and pentane should be the lowest boiling point. Ether should be the second lowest boiling point. Butanol should be next, and then so in.
Okay, you have a slide, slide 1210 on the full length slides where it shows diethyl ether as the lowest boiling point and then pentane after that.
Really? Okay. On the properties slide, let me see what the boiling point is listed there. Because the boiling point of ether, oh wow, it is 34 and 36. They are right there. So that answer is incorrect. So let me edit that real quick and change the correct answer. Because it is edit without unassigning. And if you already answered this, don't worry about it because it automatically corrects the grading afterwards. So.
Okay, thank you.
So yeah, you are correct. It's diethyl ether is 2 degrees lower. Edit. Correct answer, not correct answer, save. And that's one of the things that I liked about Top Hat was if I go back and change it to a correct answer, it actually updates the gradebook. And so everybody who got that answer correctly got it. So thank you for that. I didn't know that that was wrong. It's the first time I've heard that.
No problem.
All right. So any other aldehydes and ketone questions? All right. I'm going to be pulling up my slides for chapter 13 then. Can I? All right. So chapter 13 is a continuation of those carbonyl functional groups that we saw at the beginning of the aldehydes and ketones chapter. Okay. All right, let me start my video back up again. There we are. Okay. So I said at the beginning of chapter 12 that the carbonyl was the functional group that started out with aldehydes and ketones, but then it carried on to carboxylic acids, and we'll use it in enolates as well. Okay, so we're going to share my screen and we're going to start looking at carboxylic acids. There we go. Okay. Now, carboxylic acids are a little different than the aldehydes and ketones because instead of having a bond to a carbon or a hydrogen, carboxylic acid has a second bond to technically a third bond to an oxygen. And all the carboxylic acid derivatives here are things that are bonded to electronegative atoms. For example, some of the derivatives have halogens on them, some of the derivatives have nitrogens on them, and some of them have oxygens on them. So the entire class of carboxylic acids, it basically is a carbonyl with an electronegative atom other than carbon or hydrogen attached to them. Okay, so let's go to the beginning here. So the general functional group here is the carboxylic acid, where we have our core, which is our carbonyl, and some of the reactions take advantage of the fact that that's a partially positive carbon and a partially negative oxygen. Okay. Now, we also have a hydrogen here, and that's a hydrogen bondable hydrogen. So some of the reactions are going to take place at that hydrogen. Okay. Now, in addition to that, we have the lone pair on the oxygen. So some of the reactions can take place there as well. Okay. So the type of reagent we're going to react it with, it might react at one of those three different locations. So we need to, this adds that one layer of complexity, but we'll see as we go along, there's a reason and a rhyme to all of these reactions, and it has everything to do with acidity and basicity. Okay, and so we'll follow that as we go. So the general concept of is, anything with an R, COOH, or occasionally RCO2H, any of these are what we consider carboxylic acids. Okay, and so the R can be anything aliphatic or aromatic. It doesn't matter. When they're aromatic, we tend to put this AR, meaning an aromatic ring, like a benzene ring. Okay. So that being said, carboxylic acids are the highest priority and will name your compound, no matter what other functional groups are on there. Okay, so if you see a carboxylic acid, it's going to have oic acid at the end of it. Okay, so we're dropping the E, which was the designator for alkanes, and we added the O and E. We still follow all the other rules, where the prefix is the number of carbons we have in our chain. The infix tells us that we have double bonds or triple bonds in that chain. Okay, so those still exist, and those still are put in the same order that we did on all the other nomenclature, except now we're going to just add oic acid to the end. Okay, now a lot of these carboxylic acids, both mono and dicarboxylic acids, have special names, and I'll draw attention to a few of those because those are the ones you'll, number one, see a lot in real life, and that might be tested on in the future. So we'll make sure we do that as well. Okay, so let's go ahead and name this right here. Okay, the trick, the tricky thing you got to remember is that the carbon of the carbonyl of the carboxylic acid is always number one. Okay, and it counts to the number of carbons in your main chain. So that's 1, 2, 3, and 4. So we have 4 carbons. So we have butanoic acid. Okay, and because the carboxylic acid is the name, it's always at the 1 position, we name our substituents based on that. Okay, so in the next case here, we have 1, 2 carbons, but don't forget, we have to add that carbon of the carboxylic acid. So we have 3 carbons. So that's would be propionic acid, but we have a double bond. So it's propionic acid, propionic acid. So we have that infix of that En showing us we have a double bond. And then we have a substituent here, And our arenes, our benzene rings, are always substituents unless it's named for that, like benzoic acid. Okay, we had those in the benzene chapter. That's when they're specially named, that's the only time they take the precedent of the system. So, and we have these on opposite sides. So we have trans 3-phenyl propienoic acid. Okay, this actually turns out to have a common name called cinnamic acid, and it has a cinnamony type flavor and smell to it. Okay, so like I said before, the carboxy groups takes precedent over all other functional groups. So when we used to name something as an alcohol, it's now a substituent. And when your OH is a substituent, we call it hydroxy. And remember, we have 1, 2, 3, 4, 5, 6. So we have hexanoic acid, and that hydroxy is on the 5. So this actually makes it easier to know exactly where 1 is, because 1 is always where your carboxylic acid carbonate is. So that's great. Amino butanoic acid. And then remember, when we have an aldehyde or a ketone in the system, that as a substituent becomes oxo. Okay, so in this case, we have 1, 2, 3, 4, 5. So that's 5-oxohexanoic acid. Okay, so all the same rules, highest priority. If you see one, always name it for the carboxylic acid. I don't know why, I think it's later than it is. Okay, so now those are the monoacids, but you can have 2 carboxylic acids on a chain. Just like we had diols and triols, we can also have dicarboxylic acids and tricarboxylic acids. Here, instead of oic acid, we drop the E and add dioic acid. So you can easily name them from that. And most of the dioic acids have common names. Okay, so let's look at this first one here. Okay, we have a total of 1, 2 carbons, so that makes it ethane dioic acid. Okay, its common name is oxalic acid, and I'll tell you a mnemonic for remembering the common names here in a minute. So here we have 1, 2, 3, so that would be propane dioic acid, and it's called malonic acid. Okay. 1, 2, 3, 4, butane dioic acid or succinic acid. Okay. And the 1, 2, 3, 4, 5, pentanoic acid or glutaric acid. And then the 6 would be the adiptic acid. Okay. The way to remember the common names of these diacids is, oh my, such good apple pie. And then the pi is actually for phthalic acid. It is the benzene derivatives of dicarboxylic acids are all phthalic acids. Okay. So, oh my, such good apple pie gives you the way to remember all of the dicarboxylic acids. You have a question? Okay. So,
yes, I was going to ask, what did those letters stand for one more time?
Yeah. O stands for oxalic acid. M stands for malonic acid. S stands for succinic acid. Glutaric acid is the G. Adiptic acid is the A. And then P stands for phthalic acid. That's a dicarboxylic acid on a benzene ring. Okay. And yes, these are going to be in the book for chapter 13. But it'll give you a nice mnemonic to remember them by. Okay. Okay. So let's do one more thing about nomenclature. Just like with the aldehydes, when you had an aldehyde pendant to a ring, it was called carboxaldehyde, okay? Because the ring itself cannot contain the carboxylic acid, okay? So when we have that happen, you actually name the ring and then add carboxylic acid to the end. So it's kind of like that aldehyde pendant to the ring, but it's with the carboxylic acids. So in this case here, again, whatever the naming group is, and in this case, it's the carboxylic acid, gives you your position 1, okay? So in this case, we have a 2-cyclohexene carboxylic acid, or you could write it cyclohex-2-ene carboxylic acid, okay? And show the 2 is right next to the ene so that there's no ambiguity, okay? Now, they both work, but that's good. Okay, for this right here, we have a cyclopentane, so that's great, but we have 2 carboxylic acids, so we have to say dicarboxylic acid, okay? Then we have to pick one of them as 1, and then one of them as the lowest number, and in this case, it would be 3, not 4. And so we have 1,3-cyclopentane dicarboxylic acid. And because we have a ring, we have fixed stereochemistry, so they can't rotate, and therefore one's going up, one's going down. That makes it trans 1,3-cyclopentane dicarboxylic acid. Okay? So we're not going to lose any of our nomenclature rules here. We're just going to keep adding on to them. All right, so here's the benzoic acids. We talked about benzoic acid itself in the benzene chapter here. And when we have that benzene, it names the compounds. So this would be hydroxybenzoic acid because that hydroxy is a substituent here. But when we have 2 of them on here, I told you that was phthalic acid, okay? So specifically, they have different names, okay? So the 1,2-carboxylic acid is called phthalic acid, which is the P in oh my, such good apple pie. However, if they're para to each other, we call it tetraphthalic acid as being 1,4 position. And then the meta is called isophthalic acid. So there's phthalic acid, and then there is COOH, COOH, and so that's isophthalic acid. So phthalic acid is the dicarboxylic acid right next to each other. Then you have the isomer of it is the meta isomer is isophthalic acid, and then across from each other is terephthalic acid. In fact, terephthalic acid is used a lot in common polymers, and we'll talk about that in the polymer chapter at the end of the year, chapter 16. All right, now that's how we name it by IUPAC names. However, because they're so commonly used, especially in biochemistry and in pharmaceutical companies, we actually have a common way to name it. And when we do that common names, we actually end up, we know it's a common name because we have the alpha, beta, gamma nomenclature on it. And so the alpha, beta, gamma nomenclature is a little bit different because the carboxylic acid stands alone, and your alpha is the position 1 carbon over from your carboxylic acid. So in this case here, IUPAC wise, we would name it 1 through 5 in that direction. However, in common names, this becomes our alpha, beta, gamma, delta, okay? So when we put a substituent on there, we can tell you where the substituent is using its common name. So in IUPAC here, we would have 1, 2, 3, 4 carbons, which would give us butanoic acid, and the amine is on the 4th carbon, so it's 4-amino. However, the common name for that mono acid is called butyric acid. It actually smells very bad. It's the smell you get when butter goes rancid, okay? But, so that's butyric acid. And then this is the amino group, and it's on the alpha, beta, gamma carbon from that. So that's gamma amino butyric acid, or GABA. It's actually used as a hypnotic sleep aid for people who have trouble sleeping. Okay. So, and just like before, we have those common names. We would name them through the IUPAC names. However, there's this one common group, just like isopropyl or isobutyl group, you see in common names again and again and again. And it's this carbonyl with a methyl group on it. That carbonyl with a methyl group on it is called the acetyl group or the aceto group. And so we might see it occasionally as This is acetoacetic acid because we have the aceto group here and we have the acetic acid group here. Okay, so this is acetoacetic acid. Okay. So these are common names. You run across them occasionally. This, anytime you see a gamma or an alpha, beta, gamma, a Greek letter on there, you know you're naming it by a common name. And you need to pay attention to the names at that point. Okay. Okay, we're not going to do that. Okay, so let's start talking about the properties of carboxylic acids. So carboxylic acids are known for being very high boiling and very high melting compounds. And it has everything to do with the idea that carboxylic acid is, number one, acidic, which means it hydrogen bonds very strongly. But not only does it hydrogen bond very strongly, it actually forms a 8-membered ring, a dimeric structure. So it's a dimer, it's 2 of them put together. It forms this 8-membered ring, hydrogen bonded together, and that basically almost, imagine increasing the strength of your hydrogen bonding. Therefore, it is the one that boosts your boiling points and melting points even more than your standard alcohol hydrogen bond. Okay. And because of that, you can have a very small carboxylic acid like acetic acid or vinegar, and it'll have a very high boiling point of 120 degrees when something like, benzene has a much lower boiling point of 50 degrees, even though it has more mass to it. Now, carboxylic acids, when they're small, tend to be fairly soluble in water, and they're more soluble in water than other acids because of that hydrogen bonding. And because it's acidic, you can actually dissolve them in very weak bases and make them highly soluble in water, even if they have long carboxylic acid chains. Okay. So, that being said, what kind of bonding does that long hydrocarbon chain have? Okay. It only has van der Waals forces or dipole-dipole interaction. Okay. And the carboxylic acid, which is always at the end of the chain, has this strong polar hydrogen bondable group. Okay. So when we have that competition between that van der Waals forces that doesn't want to dissolve in water and that carboxylic acid that does want to go into water, we have, just like in the case of alcohols, we could pull in maybe 3 or 4 carbons with the hydrogen bonding in alcohol. Let's see how many carbons we can pull in with the hydrogen bonding associated with the carboxylic acid. Okay, because they are weak acids, they do get to have this resonance stabilization that lets them dissolve in water. Come on, I'm going to go back up. I'm going to go to, I don't have a boiling point or solubility study. Ah, darn it. Okay, I'm going to have to add a slide to looking at the solubility versus molecular weight. I'll add that next time, because that's important. Okay, so let's go back to looking at it as an acid. So alcohols, because it has a hydrogen bond, they are acidic. They have about the same acidity as water. The carboxylic acid, because we have to be able to delocalize the charge over 2 oxygens, are more acidic. Okay, and so for an organic compound, it's one of our more acidic ones at around a pKa of 4 to 5. Okay, so that means that in water, it's partially dissociated into the carboxylic acid's anion and the protonated water. And as such, it is freely soluble. The smaller carboxylic acids are freely soluble in water. Okay, but we can change the acidity of the carboxylic acid by having different groups nearby. Okay, so if you have a group that withdraws electron density, like a halogen or something that has a high nucleophilicity, you can pull electron density away from the carboxylic acid. And if you do, that makes it more of an anion, it makes that anion more stable, and it makes it more acidic. Okay. So this acidity has everything to do with an inductive effect, meaning it's pulling electron density through bonds. Okay. So let's look at our baseline. Our baseline here is the carboxylic acid with just a methyl group on it, which is the acetyl group, right? So we call that acetic acid. If that's the acetyl group, this is the acetic acid. And it's our baseline. It has our pKa right around 5, 4.76. So if we take off one of these hydrogens and add a chlorine to there, what's the first thing that's going to happen? First thing that's going to happen is that chlorine is more electronegative than that carbon or those hydrogens were. So it's going to pull electron density toward it away from that carbon. So it is inductively pulling electrons away from that carbon. As it's doing so, this carbon now is going to pull electron density away from the carbonyl because it's having its electron density pulled away from it as well. When it does that, that means that the partially negative charge that's stabilized over these things becomes bigger, okay? So you have a stronger partial negative charge on those sites, which means it becomes more acidic. And when we measure the pKa, we see the acidity drops from about 5 to a little over about half to about 2.86. Okay, that's just one chlorine group. And notice it has to pull electron density through 2 bonds to be able to change the acidity. Okay, so let's add one more. Let's turn it into the trichloro. So I'm going to start with drawing the carbonyl compound here. And then we're going to put the chlorine here, pulling electron density away, a chlorine here, pulling electron density away. And then we still have that hydrogen there. It doesn't do anything. And then, so that means this has to pull even more electron density away from that, making that proton more acidic. And we see another drop in the pKa, showing it's much more acidic. Okay. Now, if we do that one more time, it drops almost to 0. Remember, 0 is what we consider a strong acid. Everything below 0 is a very strong acid. So by just using these chlorines to enhance, by pulling the electron density away from them, it's giving them a higher acidity. So this is the inductive effect on acid strength in carboxylic acids. And it's any electron withdrawing group. Anything that is like a nitro group or a chlorine or a fluorine, any of those groups are going to increase the acidity of the carboxylic acid. Does that make sense right there? That you would, by pulling electron density away from that carbonyl, make that anion more stable, making that proton more acidic? Okay, and we can, ooh, all right. So, but because it's an inductive effect and because you're actually pulling it through bonds, if you move that electron group away, that electron donation, that electron withdrawing group away from the carboxylic acid, the effect drops off dramatically, okay? So, for example, let's start with our electron withdrawing group, the same one, chlorine here, but we're gonna add a carbon chain so that we can see how moving the chlorine changes that inductive effect. So just with it right here on that alpha carbon, the carbon right next to it here, we see a pKa of about 2.38. So it's stronger than acetic acid, but it is weaker than a strong acid. Let's just move that chlorine over one carbon, okay? So now this chlorine has to pull electron density through a total of 3 bonds right here. That decreases the effect. We're now almost to 4. Remember, regular is about 4.5, 4.8. So we've decreased the effect because it had to go through 3 bonds and not just 2 bonds. Okay. So let's move it over one more. So now it's pulling this way, this way, this way, and this way. It's pulling over through another bond. And now we're almost back up to not seeing it at all. because it's so far away, we're pulling so little electron density through all of those bonds that it starts to look just like we didn't have that electronic drawing group at all. In fact, when we look at our base molecule with no chlorines on there, it's only a little bit higher. So even through that many bonds, there's just a little bit of electron density being pulled through. Okay, so that means two things affect the acidity of these carboxylic acids. The direct connection of that electron drawing group, and that increases acidity. So the more of those you add, the more acidic it becomes. However, the effect diminishes the further you move it away from the carboxylic acid. So those are the two effects there. Okay, so we have the inductive effect, and then it drops off as you move it away from the carbonyl group. Okay, that being said, they are more acidic than alcohols, right? So that means we can react them with weaker and weaker bases. Okay, so let's start with a strong base. If we take a benzene carboxylic acid or benzoic acid here and react it with sodium hydroxide, it converts completely over to the carboxylic acid salt. Okay, now the cool thing about that is that this is barely soluble in water because we have 7 carbons and only 1 thing to hydrogen bond to. Okay, by making it the salt, it becomes pretty darn soluble in water and gives us this salt. So most carboxylic acids are much more soluble in water if they are turned into their carboxylate salts. Okay, this also works with other bases like ammonia. Okay, so ammonia we know is a base. It's a nice little base because it's lone pairs right here. It will undergo that same reaction to deprotonate the carboxylic acid and create this ammonium salt. So instead of producing water like we did here from the hydroxide and the proton, we're actually creating the ammonium salt as the cation to counterbalance this. Now, it's not as soluble in water as the other, but all carboxylic acids react with ammonia and primary and secondary amines to generate salts. All right. So we saw that they're acidic because they are carboxylic acids, so that's one. We can change the acidity by electronic drawing groups, and we see that they react with strong bases to generate salts that make them much more soluble in water. Okay, so, but if we took an alcohol and tried to deprotonate with sodium carbonate is not basic enough to deprotonate an alcohol. So it's such a weak base that it doesn't work. However, carboxylic acids are acidic enough to react with that sodium bicarbonate right here to generate our salt right here, our carboxylic acid salt, and carbonic acid. Okay, so that's the simplest carboxylic acid. And it's, if you look at it, it's the carboxylic acid is symmetrical because it has an OH here and an OH here. The only problem with carbonic acid is that it's not very stable and it decomposes into CO2 and water. Okay, so what you might know is that carbonated beverages, actually the actual material that's dissolved in the water there is carbonic acid. And by releasing the pressure, the reaction starts to produce CO2. That's where the CO2 comes from in your carbonated beverages, is this decomposition of carbonic acid to liberate CO2 and give water. And no, it's not toxic. So just carbonated beverages are okay. So the cool thing here is that if you have your carboxylic acid and you have bicarbonate, you can actually isolate a very pure salt of that compound and not have any counter ions and not have any reverse reaction, because you don't have a reverse reaction because the CO2 goes off and you have no acid available to you to liberate your carboxylic acid salt. Okay. So how can we take this into our advantage? Okay. Let's say we accidentally mixed up our benzoic acid and our benzyl alcohol in the lab. It happens, trust me. I've seen it happen before. Okay. As it turns out, benzyl alcohol is a primary alcohol and takes a strong base to deprotonate. Okay. But we know benzene, the benzoic acid actually is a much weaker base and, I'm sorry, a much stronger acid, and so therefore it can be deprotonated. Okay, now our primary alcohol has the same acidity as water, okay, which means we really can't deprotonate that alcohol with sodium hydroxide because sodium hydroxide's conjugate acid is is water, and the primary alcohol has the same acidity as water. Okay, so that means the alcohol cannot be deprotonated with sodium hydroxide either. So we'd have to use a much stronger base to deprotonate that alcohol. So we can use that to our advantage. So if we had our mixture of carboxylic acid and our primary alcohol here, we would dissolve them both up in a solution of something that doesn't dissolve in water. In this case, we're choosing diethyl ether. The reason it doesn't dissolve in water is we want to extract out the material using an aqueous solution of base. Okay, so we have both of these in a flask, stirring up in a liquid, and when we mix a sodium hydroxide solution and let it separate, the benzoic acid is going to deprotonate and be pulled into the water layer. Remember, neither one of these compounds is very soluble in water when they are in their protonated forms. Okay. So then, if we separate that out and took the ether layer on one side and the basic layer on the other side, that means the benzyl alcohol is not deprotonated by sodium hydroxide, so it's going to stay in the organic layer. It's going to stay in that organic solid. The benzoic acid, is deprotonated by the sodium hydroxide and therefore is pulled into the water layer. So now we have separated them by their chemical properties. So instead of throwing them out and turning them to waste, we've actually been able to separate them by their chemical properties. And then all we have to do to isolate these is to, in the case of the non-deprotonated system, we just have to evaporate off the ether and we get our benzyl alcohol out by itself. Okay. However, in this case here, in the water layer here, it's the salt, which means we have to re-acidify the solution with some strong acid. And when we re-acidify the solution, it actually comes out of the water layer now because it's not soluble in water anymore. And we can just filter off the solid and isolate that system. So we can use that physical property of acidity and the strength of the pKa's to isolate and separate these different functional groups. Okay, questions on that? Okay, got a few more minutes, so we're gonna rally on. All right, so the next thing we wanna talk about is, and this is great because it follows our sodium borohydride reaction and lithium aluminum hydride reaction. This is where it comes into practice as far as selectivity goes, okay? This carboxylic acids are actually fairly resistant to reduction. However, they are reduced by hydride transfer agents like sodium borohydride and lithium aluminum hydride. However, the carboxylic acid group is not reduced by sodium borohydride. But the carboxylic acid group is reduced by lithium aluminum hydride. Okay, so now we have selectivity again, right? We can reduce down aldehydes and ketones with sodium borohydride, but not touch the carboxylic acids and not touch the alkenes. If we want to reduce down the carboxylic acid and not an alkene, we can use lithium aluminum hydride. So let's put that into practice here. Okay. So what we have here is that if we have that lithium aluminum hydride, we only have one carbon-carbon bond in the system. Okay. which means the alcohol we're going to get out at the end is going to give us a primary alcohol. All we're going to do is reduce off the one carbonyl compound and give us 2 hydrogens to give us our primary alcohol. And just like before, it's transferring 2 hydrides from our lithium aluminum hydride here. And then we have to break up the complex with water to give us our free alcohol. And notice here that we create a couple different hydroxides here. Those hydroxides are not basic enough to deprotonate this alcohol, so we don't have to acidify. All right, so let's put this into practice again. Let's say, okay, let's say we want to catalytically, we wanted to reduce down an alkene, but not the carboxylic acid. Turns out that the catalytic hydrogenation of an alkene does not reduce down the carboxylic acid. It's too oxidized. It will not work with this catalytic hydrogenation, the platinum with hydrogen gas, okay? So we can selectively remove any alkene or alkyne from a carboxylic acid without touching the carboxylic acid. Now, let's say you had a ketone in the carboxylic acid and you wanted to reduce down just the ketone. Well, we can't use lithium aluminum hydride because that would reduce down the carboxylic acid also. So we have to use the less reactive, the one that only reduces aldehydes and ketones, the sodium borohydride. And when we do this reaction and work it up with water, we end up getting our secondary alcohol and our carboxylic acid available to us. All right, so that is, I'm glad we got to this point because it shows you why we introduced 2 different hydride transfer agents, those reducing agents, and why we can, by choosing which reducing agent we use, we can selectively hit just our alkene, just our ketone, just our aldehyde, or just our carboxylic acid. Okay. Questions on that? Okay, I'm going to stop here today because when we go through the esters and other derivatives there, there's a lot of mechanism in that. I want to do that on a fresh day. Okay, so chapter 12 homework due on Friday, and we will continue on with chapter 13 on Monday. I'm going to go ahead and stop sharing. If you want to hang out and ask a question, go ahead. I'm just going to stop.